Hey everybody, hope you had a great Thanksgiving break. And we're getting back into Unit 3. So you've got a bunch of handouts. We talked briefly about Unit 3 last class after we graded our Unit 2 tests. And, we just kind of talked about kinetic molecular theory. And I gave you a bunch of handouts that hopefully you reviewed. But I want to go over some of the key points of those handouts real quick. That's what this lesson is going to be about. And then we're going to do a kinetic molecular theory lesson after that too. All right, so let's look at those handouts. And I'm going to try to do it in order which makes sense, but try to tie things together. But let's see if it works, okay? What am I doing? There we go. Okay, so the first thing you got was the gas one-sheeter. So this has kind of all this stuff for the gas laws, the quick points of reference you need. And so you kind of want to memorize this part right here. Now, a lot of these numbers are on your formula sheet. So if you have some time, look at your AP chemistry formula sheet and see what you're given. But 1 atmosphere is kind of our normal measurement of pressure. It's not the SI unit, but that's what we kind of go to a lot of the time. So a lot of times the pressure that you're given in a question might be in atmospheres. And so 1 atmosphere is what exactly it sounds like when you're at sea level. You have 1 atmosphere, 1 Earth atmosphere on top of you, and that's basically the pressure at sea level is 1 Earth atmosphere. And that's equal to these other units of pressure. Here's what it's equal in PSI. You don't need to know that. PSI won't be on the AP exam. But if you know anything about tire pressure, because maybe you're driving around and you want to know what your tire pressure is, 1 Earth atmosphere is about 14.7 PSI. And if you know, usually your tires are in the 30s somewhere, depending on what kind of tires you have, what kind of car you have. So understanding that a little bit. Torr and millimeters of mercury are the same exact unit. And then kPa just means kilo Pascal, so 1,000 Pascal. So if we multiplied this by 1,000, that would be the SI unit of pressure, which is Pascal, okay? But it's such a big number, 101,300, that we usually denote it as kilopascal, all right? So a lot of times the gas laws are, about what's going to happen to pressure. Is it going to go up or go down? So if you want to, simplify that, pressure is going to go up whenever you increase the number of collisions you're going to have against the container, and pressure is going to go down whenever that decreases. And then if the number of collisions stays relatively the same, now it's a little bit more complicated because you have to take into account the force of the collisions. So if the particles are moving faster, they'll collide with more force and that kind of thing. But if what you do increases collisions, then pressure is going to go up, and if what you do decreases collisions, pressure is going to go down. All right, it's important to remember this equation. Most of the time you'll be given temperature in degrees Celsius, but if you're going to plug in a temperature value into one of these gas laws where you can plug in temperature, it's got to be in Kelvin. So make sure you remember the 273. So, if you're at 25 degrees Celsius, you add 273 to that, and that's 298 Kelvin. A lot of times you're at 25 degrees Celsius, which is kind of like standard room temperature, not standard temperature. Standard temperature for a gas is 0 degrees Celsius, so 273 Kelvin. But a lot of times your lab temperature is around 25 degrees Celsius. So a lot of times you'll be plugging in 298 into temperature because you're at 25 degrees Celsius. Okay. You want to think about this. If temperature increases, particles move faster. If temperature decreases, particles move slower. And then if you have 2 different particles at the same temperature, that means same temperature means same average kinetic energy. And if you have 2 different types of particles at the same temperature, which means same average kinetic energy, the lighter particle is going to be faster and the heavier particle is going to be slower, okay? Remember, we call it the how dare you rule, okay? So these are all the gas laws. And basically, the combined gas law is Boyle's, Charles, and Gay-Lussac's all combined. So if you look at P1 V1 equals P2 V2, V1 over T1, P1 over T1, if you combine those, this is what you get. And what they're doing is they're describing the four variables of gas, which are right here listed in the ideal gas law: pressure, volume, moles of gas, which is just number of particles, right? And temperature. So kind of the speed of the particles, right? Average kinetic energy of the particles. R is a constant, so it's a number that you're just plugging in. And you got to be careful which R value you use. These R values that are right here are given to you on your formula sheet. You just got to know when to use them. Like, we use this R value if our pressure is being measured in atmospheres, and we would use this R value if our pressure is in kPa. There's other R values. I think it's 62.36. That's if you would be using millimeters of mercury or torr. Okay, so the R value is just a constant. It's given to you. You just got to know which one to use. Okay. And so if we look at the different variables of gas, pressure, volume, amount, and temperature, what these gas laws right here are showing us is how the variables relate to each other. So if the others are held constant. So if we look at Boyle's law, this is the relationship between pressure and volume, assuming temperature and amount of gas, moles of gas, is constant. So pressure and volume have an inverse relationship when the other variables are constant. So Charles' law is looking at volume and temperature. They have a direct relationship when pressure and amount of gas is held constant. Pressure and temperature have a direct relationship when volume and amount of gas is constant. And then if the only thing that you hold constant is the amount of gas, that's when you would come in and use the combined gas law. You can use any unit of pressure, any unit of volume in these gas laws, but temperature has to be the absolute scale, so it has to be the Kelvin temperature. Okay. Dalton's law is pretty easy. It's just, if you know the pressures of each individual gas in your system, if you add them up, that's the total pressure. So the total pressure of a system is the sum of the partial pressures. So if you think of like the pressure that we feel in the room right now, you know, the gas in the room is nitrogen, oxygen, CO2, and some other gases. So if we knew the individual pressures of those gases, we could add them up, and that would equal the total pressure of the room. And then this is Dalton's law with mole fraction. It says the partial pressure of a gas, so it's saying the pressure of gas A is equal to the mole fraction of gas A times the total pressure. And all mole fraction is essentially percent by mole without multiplying by 100. So if I wanted to calculate the mole fraction of A, it would just be moles of gas A, whatever that is, divided by total moles. So if we wanted to figure out the mole fraction of nitrogen in the atmosphere, we could do the moles of nitrogen in the atmosphere divided by the total moles of gas in the atmosphere. That's the mole fraction. And if we multiply that by the total pressure, that would give us the partial pressure of that gas. Okay. So again, the ideal gas law here, you know, the thing to remember about this is you're going to have to use the ideal gas law when you're not at standard temperature and pressure. A lot of times when you're at standard temperature and pressure, you can use 22.4 as a shortcut. Okay. And then we have Graham's law of effusion and diffusion, and you're never really going to have to use this gas law. And so it's really just essentially understanding that if you have gases at the same temperature, which means same average kinetic energy, the lighter particles are faster, the heavier particles are slower. So the gas with the lighter particles will effuse and diffuse faster. So effusion is escaping through a tiny hole, so like kind of like how a balloon deflates over time. The gas is escaping through a tiny hole. And diffusion is kind of you know, how fast a gas spreads out. And it's based on how fast the particles are. And so the lighter the particle, the faster the particle at the same temperature. So lighter particles effuse faster and diffuse faster. Okay, so that's really kind of the gas one-sheeter outlook. So let's look at the other handouts that you got. Let's look at the gas stoichiometry one. All right, so gas stoichiometry, you know, I overheard somebody walk in and say, gas stoichiometry, I'm never going to learn about that. It's like, well, you already know how to do it, okay? So We've already done gas stoichiometry, but we've been at STP, so that means we can use 22.4 liters per mole, okay? And so now we're saying, well, what happens if you have a gas stoichiometry problem and you're asked for volume of a gas, but you're not at STP? Oh no, well, it just means you have to use the ideal gas law. So let me show you what I mean. But first is, make sure you understand the shortcut. In this question right here, 15 liters of hydrogen gas react with excess nitrogen. We want to know how many liters of ammonia gas will be produced. So what I want us to notice is that we are given liters of a gas, so volume of a gas, and we're asked for volume of a gas. If you're going from volume of one gas to volume of another gas in a stoichiometry problem, then all you have to do is multiply by the mole ratio, because the mole ratio in our balanced equation is going to be the same thing as the volume ratio for gases. It's only for gases. Because notice the setup here, we divided by 22.4 to get moles of hydrogen, and then once we multiply by our mole ratio, we have moles of ammonia, and then we multiply by 22.4. So you divide it by 22.4, you multiply by 22.4, let's just skip that. All we had to do was multiply by that ratio. So the mole ratio is the volume ratio. And that doesn't necessarily, that's not true, that's not only true at STP. If you're going from volume of a gas to volume of a gas in a stoichiometry problem, and the pressure and the temperature just stay constant, it doesn't have to be standard temperature and pressure, it could just be stays constant, all you have to do is multiply by the mole ratio, because the mole ratio is the volume ratio. Okay, so what I want us to notice is if we're not at STP. So here we're given a combustion stoichiometry problem. We want to know what volume of CO2 will be produced if 15 grams of propane undergoes complete combustion. Okay, great. All right, so we have our balanced, combustion of propane equation, and the key ratio is 3 to 1. 3 moles of CO2 will be produced for every 1 mole of propane that undergoes combustion. So if we follow our steps, we have a recipe. Now we take what we're given and convert it to moles. So this is just grams of propane to moles. This is the molar mass of propane. Then we multiply by the mole ratio, 3 to 1, 3 moles of CO2 for 1 mole of propane. If we were at STP, the very next step would be convert to desired units. And if we were at STP, we would multiply by 22.4 liters because we wanted the volume of the gas. But notice here, we're not at STP. Remember, standard temperature is 0 Celsius. We're not there. And you have to be at both. You have to be at STP. You have to be at standard temperature and standard pressure. So you have to be at 1 atmosphere and 0 degrees Celsius. If you're not at one of those things, you're not at STP, right? So we're both not at standard temperature and we're not at standard pressure. So what does that mean? It means we can't use 22.4 as a shortcut. So what we would do is we would take our moles of gas, of CO2, and how do we get the volume? Well, we're going to have to use the ideal gas law. So we're going to use the ideal gas law, PV equals nRT, and we're going to solve for V. Okay, N is moles of gas, so we plug that in. R is our constant, okay? And because we have atmospheres, we're going to use 0.08206 as our ideal gas law constant, okay? 298, what's that? That's the temperature, remember, not 25. 25 plus 273, 298. And then divided by P, our pressure, okay? And we solve and we get 43.9 liters. If you use 22.4, it would be a different number, and it would be incorrect because it's going to be a different volume when you're not at standard temperature pressure, all right? So that's all we wanted to see there, okay? So the other thing I want us to understand is a lot of times you'll be given a scenario where you're collecting a gas that's like taking part in a chemical reaction, and like the chemical reaction's bubbling through water and you're collecting the gas somewhere else. And we have to understand that when we collect a gas above water, we also have water vapor there too. So if we go back to Dalton's law, the total pressure of the gas that we're collecting is not going to be just that gas we're collecting, it's also going to be some water vapor there too. So if we know the total pressure and we subtract the pressure of water, then what's left over is the pressure of the gas you're collecting. So like, let's look in this little sample. If we do zinc, if we add zinc to some aqueous hydrochloric acid. This reaction takes place, and notice that hydrogen gas gets produced. So that's going to kind of bubble out of solution, and we can collect that gas somewhere else. But if we collect it above water, the gas we're collecting is hydrogen plus water vapor. Okay, so notice, like, so here's the reaction going on. The hydrogen gas is bubbling up, and it's going through here, and it's being collected up here. So this gas right here is hydrogen gas, but also notice it's above water. So there's water molecules that are making it. Some of the water molecules are going to evaporate, and you're going to get some water vapor pressure. And so the gas here, the total pressure, theoretically, if we knew this volume and we measure its pressure and we know what temperature is going on, we can figure out moles of gas. But unfortunately, that moles of gas isn't just the hydrogen. That moles of gas would be the hydrogen plus the water vapor that also evaporates, right? So what we would have to do is know the vapor pressure of water at whatever temperature this is, so we could subtract it from the total pressure. So if you were told the total pressure is 0.98 atmospheres, and you're told that the vapor pressure of water at that temperature is 0.03 atmospheres, all you'd have to do is subtract, and that would give you the pressure of just hydrogen. So if we plugged in that pressure into the ideal gas law, the N we would calculate is moles of just moles of just hydrogen that were produced. And now if we know moles of hydrogen produced, we could do stoichiometry to figure out how much zinc reacted or whatever, okay? And that's all based on the fact that we know liquids evaporate, okay? So anytime you have a liquid, there's a pressure above that liquid, and it's equal to the vapor pressure of that liquid. So let me just show you what vapor pressure is. So, right, if we took this beaker of water and we removed the cap, right, eventually all the water would evaporate, okay? But if you have it capped so the gas can't escape, eventually you get to an equilibrium as long as temperature stays the same. So eventually, like if you measured the pressure above this liquid, it would increase, and then all of a sudden it would just remain constant as long as temperature remained the same. And that's because you would have particles evaporating and condensing at the same rate. So the total number of gas particles would remain constant. And if the total number of gas particles remain constant in the same volume and the same temperature, the pressure would remain the same, right? And so if we leave it uncapped, we won't ever reach that equilibrium because the gas particles will just, fly away. And eventually you'll be left with no liquid there, okay? So a couple things to know about vapor pressure is the definition of the boiling point is when the vapor pressure of a liquid equals the external pressure. So there's two ways to make a liquid boil. You could heat this up, you could add heat, and what would that do? That would increase the number of particles that vaporize, and eventually, once the pressure in the container is equal to the external pressure, so let's say 1 atmosphere, then your liquids will start to boil, okay? Like, so for water, you have to heat up the sample to 100 degrees Celsius for the vapor pressure above the water to equal 1 atmosphere, and then the water will boil. That's one way to boil water. The other way to boil water would be lower the external pressure. If you lower the external pressure, then once you've lowered the external pressure to equal the vapor pressure of the liquid, that's when it would boil. So you could boil water at a low temperature because you're at a very low pressure, okay? Or you could, boil water at a high temperature because you have a high pressure, okay? And then the other thing to understand is if you have two different liquids and they have different vapor pressures, the one with the higher vapor pressure at the same temperature has weaker IMFs, because that means more particles are in the gas state. So higher vapor pressure means more particles were able to vaporize. What does vaporization mean? It means breaking the IMFs. So if more particles were able to overcome the IMFs, that means you have weaker IMFs at the same average kinetic energy, the same temperature. So higher vapor pressure means weaker IMFs, lower vapor pressure means stronger IMFs. So that's another key point to take away, all right? So those are all some just basics going into Unit 3. We're gonna come back here in a little bit with a quick lesson on kinetic molecular theory. We'll do a practice problem together that we probably will do in class, but maybe we won't spend enough time on it for you to completely understand it. So if you need some more help, you can come back and watch the video. All right, so all right, later.